What are performance and efficiency cores in Intel's 12th generation Alder Lake CPU line? I watched Intel's Architecture Day 2021 released in August 2021, last month at the time of writing this. After watching Intel's video about their new CPU, I was, quite honestly, a bit confused. I guess the new microprocessors are not going to have a 2-to-1 thread-to-core ratio anymore. Supposedly the i5 will have 10 cores and amp, 16 threads, and the i7s and i9s are similar. I just don't remember exactly what they will be. From what I understand though, the new core-to-thread ratios are the result of specialized cores. If I got this right, some cores are efficiency cores, and they have been named efficiency cores, and the rest of the cores in the CPU are performance cores, which, to no surprise, have been named performance cores. When new microprocessors are released, it can be really hard to know what names and numbers are actually based in computer science, and which ones are just a marketing attempt to make the chips look good. In other words, what I would like to know. Is there actually anything to the performance and efficiency cores, or is it just a marketing ploy? And if the two core are not just a marketing ploy, and having cores for efficiency and cores for performance is going to make a difference, then what exactly will the efficiency cores do that will be different from what the performance cores do?
It's Intel's version of ARM's Big Dot Little. You have some big cores with very good single-thread performance, but which spend significant power on wide, deep out-of-order exec, and some simpler little cores which can't run as fast, but use less energy per work. For example, an efficiency core at 2 GHz might be about as fast as a performance core at 1 GHz, but still use less power. Those numbers are totally made up, not intended even as a guess about Alder Lake. Intel has some marketing graphs. The performance, P, cores are next-gen Ice Lake cores, like in mainstream desktop/laptop/server. Specifically, Golden Cove, same as in Sapphire Rapids Xeon, but with its X512 support disabled. Unless a BIOS option disables the E-cores, or you bought a desktop Alder Lake without any E-cores, Peakworld. Hybrid chips are new and x86 hardware. Software ecosystem has no way for a process to discover that only some cores could run X512 without faulting, and libc mensp would tend to use X512 in every process if it was available, so the least bad option is to reduce all cores to their lowest common denominator. Gracemont does support a bunch of stuff like X2, so it's not dipping below the Haswell baseline, but it is a step back from Ice Lake and Tiger Lake CPUs. See the instruction sets. Alder Lake dumps X512 in a big way section of the recent AnandTech article. The efficiency, E, cores are Gracemont, latest generation of the Silvermont family, Intel's low-power CPUs. The earliest Silvermont family CPUs were pretty low-end, with out-of-order exec, for integer only, not FP/SIMD, but with a much smaller window to find instruction-level parallelism, and much narrower pipeline, fewer instructions decoded or executed in parallel. They were the successor to the original Atom, used in netbooks and some server appliance things such as NAS boxes. But with Tremont and now Gracemont, they've scaled up significantly, with apparently a ROB size, reorder buffer for out-of-order exec, of 256, up from 208 in Tremont, versus like 32 in Silvermont. See David Cantor's deep dive on it, versus Haswell. By comparison, Skylake's ROB is 224 entries, while Golden Cove's ROB is 512. Still, Tremont was aimed at low-power microservers and similar. They don't make chips with huge numbers of these cores on them. Gracemont has quite a lot of SIMD and integer execution units, and a 5-wide pipeline, at the narrowest point, allocation/rename, same width as Ice Lake. But less area spent on cache, and lower max clock speed, and 4 integer ALU ports, 2x load and 2x store per clock, 2/clock simd FP, and 3/clock simd integer ALU, same as Ice Lake. So that's a lot beefier than old school Silvermont, which were too wide. What I'm not clear on is how Gracemont is saving power versus Ice Lake. Perhaps some of its other out-of-order exec resources are less beefy, like the scheduler, reservation station, sizes for tracking not yet executed UOPs, picking the oldest UOP for each port that has its inputs ready. A big ROB can hide latency of one cache miss for a long time if most of the later instructions were independent, but a big RS is needed to overlap long dependency chains with surrounding code. For example, see this micro-benchmark experiment on Skylake, and this earlier write-up about uexec. A big RS is quite power-intensive, and UOPs enter and leave it in unpredictable order, unlike the ROB, which can be a big circular buffer with instructions issuing and retiring in program order. The Intel Architecture Day 2021 slides didn't seem to mention a number for RS size. And it might be separate scheduling queues for separate ports, unlike the mostly unified scheduler in Intel's big cores, since power scales more than linearly with size. If that sounded like technobabble but you're curious to learn more about CPU architecture, check out Modern Microprocessors, a 90-minute guide. If you already have some idea what an instruction is, and what it means for a CPU to fetch, decode, and execute one. Footnote 1, except for the now discontinued Xeon Phi compute cards, Knight's Landing was basically 72 Silvermont cores with a X512 bolted on, with a mesh interconnect and some fast cache and local memory. Motivation for heterogeneous multi-core CPUs. Lots of things on a desktop, like playing a video, animating a UI, scrolling a web page, or running spell check as you type, or running all the crappy JavaScript that shows ads, just requires a bit of CPU at very frequent intervals, so waking up an efficient core to do that costs less total energy than waking up a big core to do the same thing. The efficiency cores are optimized for throughput per die area. Improving the single-thread performance of a core has diminishing returns, for example large per-core caches, but lots of things in current computing are hard to parallelize, or simply haven't been because it's still non-trivial. Good single-threaded performance is still very important for interactive use. For literally just web browsing, I'd take a 5 GHz Max Turbo dual-core Ice Lake over a huge 40-core 2.4 GHz Max Turbo Xeon system. That's maybe somewhat unrealistic because most big Xeons can turbo a single or a couple cores to higher than 2.4 GHz if the rest are idle, but let's say 40 efficiency cores. CPUs are at the far opposite end of the spectrum from mainstream big core CPUs, near useless single-thread performance, but very good overall throughput, but some computational work doesn't easily lend itself to running on a GPU. For example, running a compiler, even though there's tremendous parallelism if you have multiple source files that need rebuilding. Having a bunch of efficiency cores should be great for stuff that does have some parallelism, again like a big compile job. And with their good amount of SIMD, FP execution units, probably also video encoding and even numerical stuff like matrix multiplies. Gracemont did add IFs2 to match the big cores. So you want at least a couple performance cores for single-threaded stuff, especially for interactive use. But once you have 4 Golden Cove cores, given the choice between 4 more Golden Cove cores or adding 16 Gracemont cores, having Gracemont cores is pretty attractive if their throughput isn't terrible. Which it isn't. Apparently that 4:1 area ratio is about right, according to Intel. Except it means you can't use the UX512 hardware that's part of a Golden Cove core, so that's a big downside for workloads that can benefit from UX512. Although unlike Skylake X, I think Ice Lake only ever has one 512-bit FMA unit, which is composed of the two 256-bit FMA units, so the max FMA throughput is the same with UX or UX512 on Ice Lake, Sunny Cove, Tiger Lake, and probably also Golden Cove-based CPUs with UX512, like Sapphire Rapids. But UX512 is nice for a lot of other reasons, and high throughput for simmed integer doesn't rely on the one FMA port. Update: if you disable the E-cores at boot time, you can use UX512. Unless you bought a desktop that didn't have any E-cores in the first place, this may not be a win for overall throughput in code that scales well to more cores. Best case is probably things where UX512 only new instructions help a lot, like bitwise boolean logged, or that are partly limited by aggregate memory bandwidth. But it could be useful for testing, tuning code that will run on servers with UX512. Some MOBO laptop vendors may not include that BIOS option, though. The existence of the efficiency cores means the performance cores can push farther into the diminishing returns of chasing single-threaded performance at the cost of power and area, since workloads that don't need that can run on the efficiency cores. Although Intel does still use the same Golden Cove microarchitecture in CPUs without any E-cores, for example Sapphire Rapids Xeon, so they can't go totally nuts here. In fact, Sapphire Rapids has 2 MB of L2 cache per Golden Cove core, versus 1.25 MB in client chips. This URL. That makes some sense given that servers are more often running multiple CPU-intensive things, so competition for L3 cache is worse, and its latency is also worse with the slower interconnect between more cores. In Alder Lake, each group of 4 E-cores shares an L2 cache of up to 4 MB. Scheduling threads to cores. OCs have to decide which thread should run on which core. Or more accurately, on each core separately. A function, for example Linux's schedule, has to pick a task to run on this core. Scheduling is a distributed algorithm, not one master control program assigning threads to cores. With cores not being all the same, it matters where a thread runs. Making good decisions can benefit from some info from the hardware about what kind of stuff a thread is doing, for example on a big core if it's running close to the pipeline with max UOPS per clock then it's fully benefiting from being there. But if it's stalling on cache misses a lot, it isn't. It might do even worse on an E-core where L2 is shared by 4 cores, instead of making OCs use PU events, performance monitoring unit, like for perfstat, Intel added a new mechanism for the OS to ask the CPU about stuff like this. Intel Thread Director is hardware and software. Unfortunately only Windows 11 will have good support for that initially. The AnandTech article linked below mentions that Linux won't have good support for it initially. Intel hasn't finished working on Linux patches to send upstream. So we might have naive thread scheduling on Alder Lake Linux systems for a while. This URL has some details. And the whole article, written August 2021, is a good read if you want to know more about Alder Lake. Also related, this URL which I've already linked a couple times in this answer for microarchitectural details.
If I got this right, some cores are efficiency cores, and they have been named efficiency cores and AM, while the rest of the cores in the CPU are performance cores, which, to no surprise, have been named performance cores. Alder Lake processors are going to have two types of cores. Only the performance cores will have hyper-threading capability. This is the reason you can have a 10-core processor which supports 16 threads. In the case of the Core i5-12600K, it has 6P cores and 4E cores. Is there actually anything to the performance and efficiency cores, or is it just a marketing ploy? Given the product has not been released, actual performance benchmarks are not possible, but leaked data from users with engineering samples indicate the performance gains are real. If the two cores are not just a marketing ploy and having cores for efficiency and cores for performance is going to make a difference, then what exactly will the efficiency cores do that will be different from what the performance cores do? The intent of the efficiency cores is they would do background tasks, of course without an OS that takes advantage of those cores. They will only be used by software that explicitly uses them. The service that handles updating Chrome likely will eventually use these cores, allowing the performance cores to handle the main threads of the browser. Image source: Intel's Alder Lake combines performance and efficiency CPU cores on one chip. ARM architecture has had performance and efficiency cores for a while now. I suspect the true reason behind Intel's decision to introduce efficiency cores is due to the fact you can only shrink your cores to a certain point, and the power required for their processors was only increasing. So by introducing efficiency cores, you can increase the performance of a processor significantly, but keep the size of the processor roughly the same. This performance increase will scale as you are able to shrink the die size of the processor. It's a way to avoid having to shrink 32 performance cores and having horrible yields. To give you perspective, the expected TDP of the Core i9-12900K is around 125W. The TDP for i9-11900K is also 125W but has 16 fewer cores. Alder Lake is expected to be manufactured on the Intel 7 process, previously called 10 nanometers enhanced superfin S. Process node names have been as much marketing as reality for some years now, and Intel's switch to names that don't even pretend to be nanometers just reinforces that. Regardless of the transistor density, an efficiency core takes less total area, die size, than a performance core, since both types of cores, and the uncore logic that connects them into being a multi-core CPU, are part of the same piece of silicon, all using the same transistors. Intel is planning chiplets for a 2023, where each core can be manufactured separately, so a defect in one doesn't ruin a whole CPU's worth of cores. Alder Lake is not doing that.
What exactly will the efficiency cores do that will be different from what the performance cores do? The efficiency cores are much smaller than the performance cores. In fact, they take up about a quarter as much space as the performance cores. The following diagram shows a setup with 8 performance cores with 8 efficiency cores. P core equals performance core, E cores equals efficiency cores. Source. What this translates to is simpler cores that can handle less instructions per second, and have limited instruction set capabilities. But the beauty of this is they use less power and we can fit so many more of them in. So what's the deal with the performance cores? Why are they so much larger? The performance cores have many more capabilities for specific use cases. They are designed to take as much power as possible, clocking up their frequency to the maximum it goes to try and get big tasks done as quickly as possible. If you haven't yet heard of a 512, This is a relatively new instruction that was added to mainstream desktop Intel CPUs, starting with Rocket Lake. It's used mainly in scientific applications and AI. Here's a quote from AnandTech describing the thermals produced from utilizing it. Within a second of running of 512 code, we are in the high 90 degrees Celsius, or in some cases, 100 degrees Celsius. Our temperatures peak at 104 degrees Celsius. The of512 instruction alone takes up a lot of space on the die. And you can bet it's included in the performance cores. Why our efficiency cores are so beautiful and boost even heavy workloads? There are two main things coming together here: size and operating frequency. What it comes down to is increased core count. Size. Because the cores are smaller, we can fit plenty more of them into the chip. Operating frequency. Because the maximum frequency of these cores is capped lower, having this many cores in a tight space isn't a problem because they generate a much more manageable amount of heat. These two properties allow us to have many more cores on a chip. More cores means more work can be done in parallel. Newer programs love to allocate additional work to more processor threads if any are available. Having fewer cores at a higher frequency is much less efficient for thermal headroom, because the amount of power required per frequency boost does not increase proportionally. Having an increase of efficient cores in parallel is the way to go.